In this video, we continue our discussion of infinite series, and we look at a second example of the direct comparison test part 1. So let's quickly recall, what did the direct comparison test tell us? Well, the direct comparison test told us that if we start with the series a sub n and compare it to a new series b sub n, such that the following conditions hold true: the terms in a sub n are smaller than the terms in b sub n, then if b sub n converges, a sub n must also converge. Pictorially, I had drawn two discs and said a sub n is smaller than b sub n, and if b sub n converges, that means a sub n must also be forced to converge in the same fashion. So let's take a look at an example. This is example number 2. Use the direct comparison test to show that the following series converges. I have the infinite series n equals 1 to infinity of 2 plus the cosine of n over n squared. Oh, how cool is that? We've got some trigonometry in this series. So, a sub n is our original series, n equals 1 to infinity, of 2 plus the cosine of n over n squared. This is our original series, which we call a sub n. For the direct comparison test, we need to find a comparing series, b sub n. Well, in this example, it's not quite as clear-cut what we should choose b sub n to be. So let's do a little thinking. What do we know about a sub n? Well, let's start with the trigonometric part of it. Let's look at the cosine. What specifically do we know about cosine? Cosine is always bounded between two numbers, isn't it? Think of the sandwich theorem from Calculus 1 if you want, right? Cosine is bounded between two numbers, 1 and negative 1. That means that 2 plus the cosine must also be bounded. It's bounded. Well, how would I get this? I would take and add 2 to all my parts, right? So 2 plus cosine n is bounded by two numbers, namely 2 minus 1, which is 1, and 2 plus 1, which is 3. So that's also a fact. Continuing, if I take and divide 2 plus cosine n by n squared, because n squared is a positive number, I can do that to all parts of my three-part inequality and not change the order of my signs. And so that tells me that I have that 1 over n squared is less than or equal to 2 plus the cosine of n over n squared, which is less than or equal to 3 over n squared. What does that help me do? Well, this was my original series, or the nth term of my original series, a sub n. I can compare 2 plus cosine n over n squared to either 1 over n squared or 3 over n squared. Which one should we let b sub n be? Well, let's actually look closer at both of these series. 1 over n squared and 3 over n squared. Three over n squared, recall, can be thought of as 3 times the series 1 over n squared, because I can take out a constant multiple from a series. So they're really, in fact, the same thing, so to speak, when it comes to what type of series they are. What type of series is the series 1 over n squared? Something familiar to us. It's a p-series, isn't it? And in this particular p-series, what is our p-value? Our p-value is 2. And when we have p-series where the p-value is greater than 1, what does that tell me about those p-series? Those p-series actually converge, don't they? So both the series 1 over n squared and 3 times the series 1 over n squared or 3 over n squared converge. So putting that fact together, so I'm going to put him in a little thought bubble because that guy stays up there for me. Putting that fact together with the order that we have already discovered, let me quickly draw my picture. Remember, in this direct comparison test, we're taking a b sub n, which we know converges. So we want b sub n to be on the outside. We want it to be larger than the a sub n terms, so that a sub n is also forced to converge. So we need that b sub n is larger than a sub n. So if I look at my order, if I have a sub n, I need terms b sub n to be larger. That means we are going to select this variation of the p-series 1 over n squared. We are going to take 3 over n squared as our p-series, which converges. And because b sub n is larger, the terms are larger than a sub n terms, and since the series b sub n converges, that forces a sub n to also converge. Let's write that out. So, let's let b sub n be the series 3 over n squared. N equals 1 to infinity. This is a convergent series by the p-series test. Moreover, we have the statement that 0 is smaller than 2 plus the cosine of n over n squared, which is smaller than 3 over n squared. And therefore, the original series, n equals 1 to infinity, of 2 plus the cosine of n over n squared converges. And it converges by the direct comparison test.